All right, so suppose the exterior temperature was equal to 1, that function f of theta. So we just continue the problem from the previous part. So in that case, let's actually find this coefficient an. And like I said before, the typical thing to do, so you can use those formulas easily, is to make the substitution x equals cosine of theta. And so then an becomes 2n plus 1 over 2, 1 over c to the n. Now the new bounds, when theta is 0, x is equal to 1, cosine of 0 is 1. When theta is equal to pi, cosine of pi is minus 1. Notice they are reverted, these bounds, because you have an extra minus. So this is Pn of x. Sine of theta d theta is minus dx. And then you can take it, you can account for this minus by reverting back the bounds. Remember, the integral from a to b is the minus the integral from b to a. So I can switch the bounds and then eliminate this negative. So that's going to be minus 1 to 1 Pn of x dx. All right, we can compute this integral right away because remember, look at the formula sheet. We have the fact that Pn of x is equal to 1 over 2n plus 1 p prime n plus 1 of x minus p prime n minus 1 of x. So you can kind of have an antiderivative for this when n is equal to 1, 2, 3, and so on. Now remember, in my case, n is from 0, 1, 2, and so on. So if I'm going to apply this formula, the case n equals 0 is to be treated separately. Because when I plug in 0 for n, again, that's p negative 1, which doesn't exist. All right, so an, assuming n is just from 1, 2, 3, and so on, according to this formula, that's going to be 2n plus 1 over 2, 1 over c to the n. And let's plug in this antiderivative, basically, 1 over 2n plus 1 p prime, that's under the integral, p prime n plus 1 of x minus p prime n minus 1 of x dx. And let's pull out the constants. These two cancels, so you're left with 1 over 2c to the n. And then the antiderivative, Pn plus 1 of 1 minus Pn minus 1 of 1 when you plug in 1, and then subtract Pn plus 1 of minus 1, minus minus becomes plus Pn minus 1 of minus 1. Remember, by definition, the polynomial of 1 is 1. And also look at the formula. At minus 1, you also have a formula that Pn of minus x is minus 1 to the n Pn of x. So let me write it down here. Another formula is that Pn of minus x is minus 1 to the n Pn of x. So look at the formula sheet and notice that that formula as well. So over here I have minus 1 to the n plus 1 plus minus 1 to the n minus 1. These are actually, these two cancel out if you look carefully. So if it's not clear yet, if you pull another minus with the existing minus, that's actually minus 1 to the n. And if you pull out minus 1 to the negative 1, that's a minus sign, which is minus 1 to the n. And you'll see that actually that's not surprising. I mean, I did this integral with all the steps like that to illustrate how the mechanics works. But it's one of those things in which if you understand the physics or you pay attention to the physics meaning of the problem, Actually, that wouldn't be a surprise that all these coefficients are 0, except one of them. Remember, the case n equals 0, it's still to be treated separately. So going all the way back to these coefficients, let's do a naught separately. So a naught is 2 times 0 plus 1 over 2, 1 over c to the 0, and the integral from 0 to pi, p naught of cosine of theta, sine of theta, d theta. Or you could go all the way back to the integral in x. You could do that as well. So that's going to be 2 times 0 plus 1 over 2, which is 1/2, 1 over c to the 0, the integral from -1 to 1, p naught of x dx. Now, p naught is just 1. The first Legendre polynomial, oops, that's out of range, sorry about that. So the first Legendre polynomial is 1, and the integral from -1 to 1 of 1 is actually 2. So the coefficient a naught is equal to 1. But what that means is that in this case, the steady state temperature, so if you go all the way back to the formula for the solution, which is u of r theta equals the summation of an r to the n pn of cosine of theta. All the coefficients are 0 except the first one, which is 1. So it's just 1 times r to the 0, p naught of cosine. So that's just 1. So this tells me that the steady state temperature in this problem is equal to 1. Now, why is that not a surprise? Well, let's actually think a little bit what happens from a physical perspective, right? So you have a sphere, and you are under the assumption that at all times the exterior of the sphere is equal to 1, the temperature of the exterior of the sphere. So basically, at the start of the experiment, before the heat temperature stabilized in time, you have the condition that on the exterior of the sphere, so I should put here c theta, right? So when r is equal to c, you maintain at all times the temperature to be 1. Then you assume that eventually the temperature stabilizes. So eventually it won't depend on T anymore. And then the question is, what's the temperature in the interior of the sphere? Again, assuming that at all times we have the temperature equal to 1 degree on the exterior. So how would we imagine a device that keeps while the heat flows in the interior of the sphere? How do we imagine a device here on the exterior that keeps the temperature equal to 1? Well, let's say in the beginning, somewhere here in the interior, but close to the surface, you have higher temperature. So bigger than 1, close to the boundary. Now the heat flows across the radius, right? So let's say at some point, the heat flows and then it comes with a higher value than 1 in the inside, close to the boundary. Well, to maintain temperature 1, the device on the boundary needs to bleed some heat, right, so that it doesn't go above 1. Let's do in the opposite way. Let's say you have a cooler point in the interior of the sphere, less than 1 basically, so a cooler temperature. In order for the heat to not decrease the temperature, because it will decrease if the surface is basically hotter than the point on the interior, some more heat should come in to compensate. So in other words, if the temperature in the inside of the sphere is bigger than 1, the system here needs to bleed a little bit of it so that the exterior is kept at 1. If you have a cooler temperature in the inside, the device on the exterior needs to let some heat in to compensate, and then again the temperature to be 1. So as this process goes on, notice that the only situation that stabilizes the flow is to have at some point everywhere in the sphere the temperature to be equal to 1. As long as you have a point of a different temperature, then you'll have some heat flow across the surface, in and out, depending on the value, so that the temperature on the exterior can be maintained at 1. So actually, again, if you learn your physics well, and someone says, I have a sphere with the temperature 1 on the exterior at all times and no other conditions or assumptions, what's the steady state temperature? Well, it has to be 1 everywhere. You don't have to trouble yourself with the solving the boundary value problem and the Legendre polynomials and all that kind of stuff. In other situations, of course, it's less obvious and not a trivial value like in this case, and in that case, obviously, you have to do the work. So in this part, let's comment a little bit on what will be the difference if you have, going back to the hemisphere, what if you had on the boundary on the bottom Newman type of condition. So in the problem we had in the last lecture, right, we had a hemisphere, radius c, and because we have a hemisphere, then the domain for theta was pi over 2, 0 pi over 2. And again, let's say on the exterior of the sphere, we have some prescribed temperature that depends on theta. But the bottom, the flat bottom, let's say it's insulated. Well, if it's insulated, then you would write that condition as u partial r of r pi over 2, theta pi over 2 indicates the flat bottom, equal to 0. So the only difference is that when you do your separation of variables and when you deal with the Sturm-Liouville problem, then the condition will not be h of pi over 2, but h prime of pi over 2 equals 0. And of course, the equation in R will be the same as before. And so now the eigenvalues are the even ones. So if you go back again to the handout on the Legendre polynomials, let's see, on the third page, that's part C of that formula. So if h prime of pi over 2 equal to 0, then the eigenvalues, which you can call them lambda 2n, are 2n times 2n plus 1. And the eigenfunctions will be the even Legendre polynomials evaluated at cosine of theta. That's the only difference. Characteristic equation for this, right? If you plug in 2n times 2n plus 1 for lambda, the characteristic equation will be s squared plus s minus 2n plus 1, and Rn of little r will be again an r to the 2n bn r to the minus quantity 2n plus 1. Just like before, the coefficient attached to the negative exponent needs to be 0 for continuity, and your solution via superposition principle will be summation from 0 to infinity an. Let me actually keep track of this. Let's say a2n, right? I mean, it's not a big deal, but I think it's better to be consistent and actually use 2n index for all of these guys, because you go to the even coefficients only. So a2n r to the 2n p2n of cosine of theta. And then when the time comes to find a2n, you plug in c for theta, and then the question is to get f of theta in terms of an even Legendre series. All right, and then if you look at again on the formula down below on the same page, that's part B basically. The even Legendre series formula for the coefficients are that the coefficient itself is equal to, let's see, 4n plus 1 integral from 0 to pi over 2 f of theta p to n of cosine of theta sine of theta d theta. And again, if you have to do this by hand, you will make the substitution x equals cosine of theta. So if you make the substitution x equals cosine of theta, this integral becomes 4n plus 1, the integral from 0 to 1 now, f of inverse cosine of x, yeah, because theta is going to be inverse cosine, and then p to n of x dx. But again, if f of theta is not specified, you will leave it in that form. And again, just because I remember now very well, remember in the book, sometimes they will call this coefficient, they will denote by a to n this entire coefficient. So maybe I should just make a remark here. If you basically call this integral, if you denote this integral by b to n, then your coefficient here will be 1 over c to the n b to n. So be aware that when they give the answer, that's not mandatory, it's just a little gimmick of notation here. But when you see this over c to the n in the answer, it's because of this, because of them denoting the integral by b to n, rather than in my case when the integral stood for the coefficient of p to n. So that's why in their case in the answer, you will have c to the 2n popping up there. So I'm going to finish with the third part just to go over some hints on the homework, and depending on what we're going to talk about in the last week, Wednesday and Friday, we're going to, I'll see if I'll add another one, but well, there will be just one short part left for today, so stay tuned.